In software engineering, risk management is rarely a static document you write once and file away. It is a continuous background process that runs parallel to your code throughout the entire project lifecycle. Think of a doctor treating a patient. They don't just look at a person and immediately start prescribing medication. They execute a multi-step diagnostic loop. First, they identify the symptoms. Second, they diagnose the core disease. Third, they determine the treatment path. And finally, they monitor the recovery. Software project managers execute this exact same diagnostic logic, just applied to servers and codebases instead of organic biology. Human error and technical failures are inherently chaotic. To survive them, we have to translate these standard management steps into a rigid, executable mathematical algorithm. In this lecture, we will define the precise mechanics of that algorithm, detailing how engineers track, prioritize, and neutralize project threats long before they can compromise the system. By treating risk as an operational loop, project managers establish a system for handling exceptions before they manifest as critical failures. The first phase of this algorithm is risk identification. This is where we systematically answer a single question: what can go wrong? The objective here is to generate a comprehensive master list of every potential threat to the system, capturing everything from sudden customer requirement shifts to total server crashes. To populate this list, engineers typically iterate through 4 standard data gathering techniques. First, brainstorming sessions, where the development team aggregates potential failures, like poorly optimized databases. Second, expert judgment. This involves querying senior engineers to pull historical context on past failures. Third, parsing historical data from past project autopsies. And fourth, iterating through standard industry checklists covering budget, staff, and security vectors. If a risk variable is never identified during this phase, it cannot be managed. It becomes a fatal blind spot in the project architecture. But a raw, unorganized list of catastrophic threats is useless on its own. We have to analyze the severity of each threat to determine our processing order. This graph illustrates the 2 key variables required for risk analysis. On the y-axis, we plot probability, which is the likelihood of a risk executing. On the x-axis, we plot impact, representing the potential damage to the system. To establish our parameters, heavy rain during monsoon season carries a high probability, whereas an earthquake happening tomorrow has a low probability. For impact, a jammed office printer ranks incredibly low. A complete database failure ranks incredibly high. Risk prioritization calculates the product of these 2 variables. By mapping probability against impact, we mathematically sort which risks demand our immediate attention. This formats our data points into the probability impact matrix. Let's look at the extreme ends of this matrix. The highest priority zone sits at the intersection of high probability and high impact. Scenarios in this sector, like a client known for constantly changing requirements mid-sprint, require immediate planning and dedicated CPU cycles to manage. Conversely, the low probability, low impact zone down at the bottom left covers minor anomalies, like that jammed printer. These require minimal concern. Then there is the dangerous outlier, low probability but high impact. An event like full database corruption is rare, but because it can terminate the entire project, it demands strict contingency plans. Prioritization is ultimately an exercise in resource management. It stops teams from burning hours on trivial bugs while critical threat vectors remain exposed. Once our risks are sorted, we enter risk response planning, also known as risk mitigation. This is where we write the exception handling protocols for when a risk actually executes. Mitigation rarely deletes the risk entirely. Instead, it is designed to minimize the blast radius or reduce the likelihood of the event occurring. Managers use 4 strategic responses, the ARTA framework. First, avoid the risk by altering the plan to eliminate the root cause. Second, reduce the impact, like scheduling automated daily backups. Third is transfer, which shifts the liability to a third party through insurance or a cloud provider's agreement. And finally, accept. Sometimes fixing a minor risk costs more than the potential damage, so you ignore it. Before a single line of code is written, every high-priority item identified on the matrix must have an assigned ARTA protocol. All of these variables, priorities, and calculated mitigation strategies now need to be stored in a centralized data structure. This is the risk register, the master database tracking every vulnerability's precise state. For a hospital management system, we'd log a database crash, tag its medium probability and high impact, compute its high priority, and lock in daily backups for mitigation. This brings us to the final phases: risk monitoring and review and control. Because project environments change constantly, the register must be updated continuously as old risks die off and new threats emerge. We can codify this continuous methodology into an algorithmic loop. It starts with initialization, populating the risk register with brainstorming data. Then we enter a core while loop. Until project completion, the team continuously analyzes priorities and applies mitigation strategies. Inside that loop sits the monitoring function. If a sudden mid-project threat is detected, like a zero-day cyber attack, it is immediately appended to the register, and the loop iterates again. Risk management is exactly this loop. It is a persistent background function that adapts to changing project states until successful deployment. Let's look at a dry run simulation for a new food delivery application to see this algorithm in action. Mid-launch, a critical crisis occurs. The primary payment gateway fails.